produce some spatial features, learn some spatial information, and submit that learned information to a neurons, and that neuron will basically capture that spatial information inside the image. So similarly, we will be having multiple filters. Those will convolve over the image and try to learn the spatial information inside the image. Okay, so one filter would convolve over the entire image and try to produces these feature map. Then we will be having one more filter, one more filter, and one more filter. So there, like this, there could be so many features map we can produce, and each feature map will contain some of the information related to the objects inside the image. And we call these as a local features, local information. So that from local information, we'll try to learn the global information. So and these filters specially share the parameter with each other. Can somebody tell me what is this special sharing of parameter of these filters? Anyone? It could be wrong answer as well. Can you hear me?
Yes, probably
Yeah.
each filter, for example, one filter
Hmm.
is convolving over entire the image. It
Hmm.
may read some brightness or whatever in
Hmm.
form of some number it has, and it will
Hmm.
share to the next filter, I guess,
It will share to the next filter.
or new. It will
Ah,
share. It
okay.
is share in the neuron.
Okay.
Save
Anything
as in the
else?
neuron.
Anyone else? Someone else want to comment on this? How a convolution neural network share parameter and how they are different from neural networks. So let me refine it for you. Any answer from anyone? Guys, come on, you are listening the course from last few days. I have gone through the brochure. So it's a very simple thing. Hmm? Any answer? It could be a wrong answer. Please come and speak up.
Please repeat the question. Can you please repeat the
Yeah,
question?
yeah. The question is why and how convolutional neural network are different from neural network, and what is the meaning of this spatial sharing of parameter of each filter?
So spatially means in space, so it basically means the coordinates or dimensions in that sense, I guess.
Okay, so basically spatial sharing of parameter means what will happen. So let's say we have one filter. Okay, so that filter will first try to look inside one patch of this image, and once it has learned that patch of the image, it will try to understand the next patch of the image. It will convert to the next patch of the image, then next patch of the image, and try to understand whatever the spatial information the image has. So basically what has happened, this filter is being shared among all the parameters that those we wanted to interested to learn on this image. So that is the meaning of spatial sharing of the parameter. While in fully connected neural network, these things doesn't happen, right? So what happen in fully connected neural network? A particular image pixel is directly connected to the neurons, and they are interconnected with each other. That's why they don't learn spatial information. So with spatial information, you understand? You understand spatial
Yes, sir.
information? Yeah.
Yes, sir.
So spatial information, the image or object inside the image, that is spatially how it is, where it is, what it looks like. So that information is called spatial information. And that's why convolution neural network help us to reduce the number of parameter in compared to neural network if they have of the equal size, because they are going to share the parameters. But if we increase the number of layers in the networks, then definitely our number of parameters are going to increase. But they are very good in learning the spatial information. Okay, so this is what I was talking. In fully connected neural network, what will happen? We have set of input features and they are directly connected to each node. They don't share among each other, but they're fully connected to each other. So that's why they have lot of parameters, and it is very difficult to learn the spatial information. So they don't learn spatial information of an object because they are already connected with each other. and many parameters. Okay, so that is the main difference between fully connected neural network and our convolutional neural network and how they learn actually. So this is a simple architect of how multi-layer perceptron model that you can think of. You can see they are connected with each other. So there is no parameter sharing. Wherever in our convolution neural network, one filter will convolve over the entire image and use the same parameter. So what is a filter? Basically, it is again a set of a metric value, right? So those matrix values will convolve over the image and they will remain same for initial learning, and later they will changes based on the propagation, back propagation is being performed inside the network. But they will be shared among all the patches inside the image. Okay. So some examples of the filters, how filters looks like, what they do basically. So for example, I want to sharpen my image, right? Sharpen means you can see I want to highlight some of the important parts in the image. So let's say I have this kind of a filter. So a 3 by 3, it's a kind of a matrix. So when you convolve this matrix over to this image, you will see the image get sharpened. So every filter has its beauty. They can learn different kind of information from the image. So for example, I want to detect some edges in the image. So let's say I have this filter. This filter is not a random number actually. A lot of research has been done, performed to come up with these numbers actually. Okay. So when you convolve this filter over to this image in a sequential manner, the output would be like this. So you can see the filter has tried to show us the prominent edges that after convolving of this filter with this image. Similarly, if I want to find out the strong edges, then I will try to have this filter and I will try to convolve it and I will get these kind of results. So you can see how a particular filter, when it convolve over the image, it will give me the results. So can somebody tell me what are the challenges with this approach? If we want to detect some object, then what are the challenges in this approach? As in the sense of if I want to uh, design some generalized method, then what could be the challenges?
Sometimes an image contains more than two objects and they are sort of overlapping, so the edges may not be distinct. We cannot resolve them.
Not in terms of edges. Let's say anything you want to learn. Let's say you want to recognize some object in the image. Okay. And to recognize an object in the image, you may need a lot of information, right? Maybe you need, let's say you want to recognize a person, human face. Okay. So for that, you need a lot of information like outer boundary, ear, nose. So, so for that, you may say you need how many filters, how many different kind of filter we need. So you can see this filter only try to sharpen the image. This filter only try to detect the edges. This filter try to detect the strong edges. There could be another filter that will try to understand the let's say contrast variation. There could be another filter that could be try to understand the boundary information. So likewise, this we will be having so many filters, right? So what is the major challenge with this approach?
Sir, maybe we need n number of filters. That n can be any number, so that the computational time will be more.
Right. So for to solve this problem in this fashion, we call this kind of approach as handcraft engineering approach, where we design some method, some filters, particularly to solve one particular problem. Okay. And that is challenging because once your data set get changed, you will get some different kind of images. Then those set of filters may or may not work. So that is the one of the challenge. So that's why to overcome these, we have the new technology that is convolutional neural networks came into the picture where we are not going to learn these handcrafted features at all. These features will be get learned automatically through the convolution process. We are not going to define these numbers. We will let the convolutional neural network to learn these features automatically to solve a particular problem. depending on the problem. If you're going to classify human faces, then we'll try to learn features based on that. If you're going to classify dogs, then they need some different set of features. If you try to recognize fingerprints, then they will try to learn different kind of filters. So this is how CNNs are robust to different problems, and they can work in all the areas where we don't need to explicitly define that what I want to learn based on the data set and our labels, that this is what I want to learn. Those filters will automatically get learned. Do you understand this basic concept?
Yes, sir.
Okay. So the key idea, so what is the key idea is that we will design a convolution neural network that will learn features at different hierarchies. Okay. So for example, so let's say you want to learn the facial structure of humans, right? So what will happen? The lower level features. So what would be the lower level feature? The very sharp edges, boundaries, curvatures, dark spots, bright spots. So these are the very low level features inside the image. Okay. So the initial filter will try to learn up those low level features. Then the next few layers will we will say middle layers or mid level features, what they try to learn: eyes, ear, nose, etc. And then the very high level feature or abstract level features are the facial structure. So this is how CNN will try to learn or understand different features inside the image. So from edges to eyes, ears, nose to facial structure of the human. Okay. So this whole concept will you will see in the next process how CNN get works. Okay. A very simple building block of CNN. So these are the main two or three components every CNN you will see will be having. Okay. So the very first thing is you need to input the data, and CNN require CNN performs supervised learning or unsupervised learning.
Unsupervised learning.
Unsupervised learning. So what do you mean by unsupervised learning?
So the machine will detect by itself the similar things. We will not
Okay.
label this as that.
Okay. So let's say you want to understand some digits. So let's say there are digits. There is an image, it has one digit. So do you know to solve this problem, we need to label the images or not? Do we
If
need to?
if for example, in the case of digits, if the machine, because we know the digits, we can
Mhm,
label it so that it will be supervised learning. But in
mhm,
case of pictures, I think we the system, how the systems is, we don't know. Like, so for example, if it is a sharp edge,
mhm.
the machine will detect it as and save it as a number. And if the similar kind of sharp edges, if it sees anywhere else, so it will understand it as a similar object, and it will learn itself that these are the similar kind of things. So I think it is a
So
unsupervised learning.
let's say the image has a digit 3, and it says that I have detected 1. Then how we come to know whether it is detected correctly or not if you're not going to label it? Any answer from anyone? It's not one person has to speak.
So, but we divide our like into training sets and testing sets. So according to that, we might know that
So even if it is a testing set, do we need to label it or not?
in unsupervised learning, we don't label. Instead, we cluster them.
Okay. So this CNN for classification will be unsupervised or supervised? Again, I'm repeating.
So it would be unsupervised. It will learn by itself.
Okay. So
We
so
keep on
so
reiterating the model. Uh, After n number of epochs, it will generate like.
mhm. So it will keep iterating till what? How it will come to know that this is the end and I don't need to further learn?
So we'll plot it using a confusion matrix, and that will tell us like how many of our like true labels are there
But
and
you
how many
said
of.
but you said are not going to label it. It will work in an unsupervised manner.
Oh, yes, yes.
So if it is unsupervised, you can't plot confusion matrix.
So it's supervisor.
It's supervised. Okay. So basically, it has to be supervised learning because so it will see something. So here the learning will perform. It will learn automatically that part is here. So whatever it will learn, it will generate some class probability in the last layer. And finally here, let's say it will say digit 3 and here it is digit 1. So uh, what will happen? We will try to compare that the image having digit 1, the 1 class should get activated. But if it is a 3, then what will happen? It will do the back propagation. So that's why we compute the loss function, cross entropy loss function for this and try to update the weights and biases and these filters weights gets changed so that it will try to converge toward that this is not a 1, this is a 3 number. Okay. So it is a supervised learning. It's not a unsupervised, but this learning is automatically learning. That's why we are saying because these filter we are not going to fix them. They will change based on the error that will back propagate to us. Okay. So this is the one part. So convolutional feature map. So as I mentioned, there will be n number of filters. Each filter will convolve one by one and will generate a feature map. So this is a feature map for filter one. This is a feature map for filter two and three and so on. This is how does it work. Then every convolution features, once we will perform the convolution operation, will perform some activation method. We will use some activation method. So generally we use ReLU method. So ReLU is a very good between the network, between the layers, middle of the layers, we use ReLU as a activation function. Can someone tell me why we use this activation method or what are other methods?
So there's sigmoid for logistic regression, and we have linear methods for activation as well.
So there, but we will not use linear method because we want to introduce the non-linearity in the network. Why we want to introduce non-linearity in the network?
So because the nonlinear curve, they have curves. Like a straight line will not have many points, but a curve will like cover more points.
So basically, every every problem in the real world, if you will see, they are very complex in nature and they are non-linear actually. Okay. So if we try to make them as a linear, then there is a no need to learn the convolution neural networks and all that stuff because non-linear problems are being solved by these methods. Linear problem will be a straight linear regression. It could be solved using that y is equal to mx plus c, right? It has only one dependent variable. But in real world, if you want to understand something, there are n number of parameters those network has to learn. As we have discussed, we need to direct the nose, we need to direct the mouth, we need to direct the hair, and they will change for every image as well. So you can see there are n dimensional parameters we need to learn. So that's why we need to learn the non-linearity in the image. So that's why we use ReLU as the activation method. So sigmoid is a activation method, the 10H, leaky ReLU, there are so many. Okay. But most commonly ReLU is used. Then we perform the pooling layer. So what is pooling? Generally we'll say, can you mute some? Okay. So pooling is basically down sampling operation that will perform on each features. So why do we perform pooling? Any answer? Why we need pooling? So you might have heard about max pooling, mean pooling. What is pooling basically?
Sir, as you said, pooling is like downgrading.
Hmm.
So for example, in max pooling, for
Hmm.
example, in a matrix, it will take the maximum number and
Hmm.
downgrade the number of
But
features.
why we need that?
So,
There should be some reason, no? Okay. Any answer?
So to reduce the dimensions, I guess.
Yeah, this is one thing to reduce the dimension, but why we want to reduce the dimension?
To simplify our problem.
If we simplify the problem, then how it will learn the complex problem? Problems is a problem, right? We can't simplify the problem. Problem will remain problem whether it is a simple problem, hard problem, or whatever it is. Okay, we'll come to this. And then finally, we will be having a fully connected layer. Why we need fully connected layer at the end?
Each and every feature map is associated with a different attribute, and at the end we want to construct the whole image so that we can identify or classify it. Like a pizza is a pizza, we want to like, okay.
Hmm. So basically, if we are going to use CNN for classification purpose, then we have to define first how many classes we have. Okay. If you are going to classify dog and cat, you will be having two classes, right? If you're going to specify male versus female, you will be having two classes. If you're going to understand a MNIST digit data set, it has digits, let's say 1 to 10, then you have to specify that the final output will be 0 to 9. So there will be total 10 classes. Okay. So every classification problem will be solved like this. Okay. So that's why at the end we'll be having a finally fully connected layer, and that layer will be having a softmax function embedded to that, and it will generate the probability. So if I give a digit 3, it will highlight the the neuron with the 3 number is having the higher probability. Okay. And that will give us the result that this image belongs to this class. This is how classification does work. Okay. So that's why we need fully connected layer. Another simple examples of a simple convolutional network. So as we have seen earlier, so it is a combination of con layer, ReLU, con, ReLU. It will be combinations. Sometime we do pooling at here, sometime we do pooling after some few layers, some blocks. Sometime we don't perform pooling, sometime we perform some different things. So we'll see different architecture and methods to understand this. And the final layer would be fully connected layer. Please remember this. Based on the number of classes your problem have, you will take as many number of fully connected neurons in the last layer. Okay. So if it is a car, then for the class, a car class, it will give the highest probability. If it could be a truck, then it might have given a more probability. So you can see for other classes also it will give some probability, but we'll take the argmax of the final layer and will give the probability of the highest class to us. Hmm? So this is how convolution neural networks looks like. Okay, so convolution operation, I think you might have already heard about this, how convolution perform. So basically we have a filter, we have a image. So you know this operation, right? So we'll take this row, multiply with this, it will come with one number, that is one. Then we take this row, multiply with all these numbers. So it will be again one. Okay, then it will take this one and multiply with all the numbers. So we'll get one over here and one over here. So total 1, 1 plus 2. So what would be the output? 4. Do you understand this maths?
yes, sir.
Right? So this is how a simple convolution operation work. Then what will happen? There would be a stride 1. Stride 1 means we will shift this filter to the next patch. So it will be shift toward the right. So next it will convolve over this region and produce another number. Then we will shift to right side one more step and it will be produce another number. Like this convolution operation get performed. And in case we want to have the same size after convolving, there are so many other methods like keeping the padding same valid. So it will fill up all the boundaries with 0. So that the output feature map would be having the same size as of the input image size if you want, right? So this is how simple convolution filter work. This is what we use ReLU or softmax or sigmoid as a to introduce the non-linearity in the image or in the network. So basically, how does it work? It will take the value of the pixel, and for if it is a positive value, it will uh, generate the output as it is. But if it is a negative value, it will set it as 0. So you can see this graph. So if it is a positive value, it is a positive number, it will generate a positive value. A value would be as it is. But if it is a negative value, it will just completely set 0. Okay. So you can see how ReLU will help us to introduce the non-linearity in the image. Okay. So and here you can see also, so how we use in the TensorFlow. So we have a session in the evening. Over there we'll try to understand how we'll implement these methods. So tf.keras.layer.relu will give us this ReLU method to us. Okay. And this is what we were talking about, max pooling or pooling, right? So pooling could be of many type: max pooling, min pooling, average pooling, global pooling. Okay, so as we were discussing max pooling, so how does it work? It will divide the entire region into different grids. So if I am taking a max pooling with 2 cross 2 filter, it will divide like this. If I will take 3 cross 3, it will divide in another way. And stride is 2. Stride 2 means if I place my filter over here and then next in the next move, it will move by 2 pixels. So that is the meaning of stride. Okay. So what I do if I take a max pooling, so out of this grid, it will take the maximum number, that is 6. In this grid, it will take the maximum number as 8. In this, it is 3. In this, it is 4. So this is how max pooling will work. So one of the student has mentioned it will help us to reduce the dimensionality. That is very right, because whatever the feature map we will be having here, it will just produce the half of the size of that feature map. The another advantage is it will help us to introduce the spatial invariance in the network. Now, who will help me to understand this? What is this spatial invariance? That is very important actually. I think I need to share another way. Just a minute. Just a minute. Okay, like this, I can see you as well. Okay, anyone?
Sir, spatial invariance, probably. So because, for example, in the first set it is picking 6, in the next set it is picking 8, which means it is picking all the brighter spots. So which means all the there will be less variance among the total picked uh, values. So there will be
Okay.
less variance.
One simple question. So let's say I have an image of a cat. Hmm? So I have a complete data set and it has so many images of cat versus dog. Okay. So I have two classes, cats and dog. So it may be happen in one image, the cat is on this side of the part. In another image, it could be happen, the cat is on the this side of the image. In another image, it could be at the center of the image. So can you relate this spatial invariance to this example?
The pixels of the cats are not changing. They are invariant in that sense. Like if it's
Uh,
located on the left side, it's located on the left when we pull it.
so basically, the meaning is we'll try to make our network robust to these changes actually. If my network will only learn the images on the left side, then it means it won't be able to understand if the cat is on the right side of the image. It won't be able to understand it actually if we will not introduce this pooling layer inside the network. So you try to understand, it will just try to look into the patch, and from that particular patch it will try to just pick up the maximum value or it could be a minimum value depending on what we want to learn. And because it is a prominent feature inside that patch actually. Okay, so irrespective of cat would appear at the center, right, left, or anywhere in the part, it will try to learn that feature. So that's why we need this pooling layer. Okay, I hope you got this term spatial invariance. Okay, so similarly, we will be having another kind of average pooling, global pooling to help the network to understand this spatial invariance in the network. Okay, all about this, just to sum up. So we'll be having a convolutional layers that will learn these features. Then we introduce nonlinearity. So real world data is nonlinear. Okay, whatever the real world problem you're going to work, it was going to be nonlinear in nature. And pooling layer will help to reduce the dimensionality and preserve the spatial invariance with pooling. Okay. And finally, the last few layer would be a kind of a classification network. So network will be having two parts. One is this feature learning and one would be our classification stage. As I mentioned you, it will contain fully connected layer. And at the end, there would be a softmax layer, and that softmax will give us the class probability of that particular layer. Anyone having any doubt over here, please discuss, because now we're going to move to some complex networks. If you have some questions, you can ask here. If you are not going to ask, then I will ask. No questions? Is everything is clear?
Yes, sir. Please continue, sir.
Okay. So why we need flatten layer over here?
But actually, the output from the polling layer, it will be like three-dimensional, I mean, matrix format. So to give the input to fully connected layer, we need to convert into 1D format. For that, we'll be using the flatten layer.
Yeah, very right. So basically the filters, information, feature learning that we're doing, it's in the form of 2D or 3D, right? Now, a fully connected layer or neural network process information as a 1D vector, complete 1D vector. So we can't pass this information as it is. We need to flatten this. So there is a layer flatten inside the CNN that will try to make a 1D vector out of this information. And then this information is passed to the fully connected layer. Right answer. So every CNN you will see, it would be having this flattened layer, fully connected layer and softmax layer. And this part will vary depending on the kind of CNN architecture that you're going to use. Okay, good. This is just a simple explanation in the form of code. So we'll learn in our evening session that how to code this CNN network. So these are some TensorFlow and Keras are the libraries that have these kind of features to create these kind of models. So we will create a sequential model. We will add a con layer like this. Here 32 represent what? What is 32? Many of you already aware of this.
Size of a matrix.
No, it's number of filters. Okay. Number of filter a con layer would have. Filter size 3 indicates it's the size of matrix that is 3 cross 3. Then activation method. Then max pooling layer. Then you can add some railway activation function like this, or you can embed in the con layer as well. Max pooling layer, flatten layer, dense layer, right? And always remember in the last dense layer, the activation would not be ReLU or sigmoid. It would be softmax. So try to understand and explore it. Why we need softmax at the end of this layer. I will ask you guys this question in the evening session. Okay. Just note it down why we need softmax activation function in the last layer. I'm not going to discuss right now. Okay. Okay. So let's move to some of the architectures of CNN. So how computer sees objects. So objects can be anywhere in the scene. That is one thing. It can be of any orientation, it could be any rotation, it could have any color or anything. Okay. So how to overcome these challenges? These are very complex things, right? So you can see this is a bicycle, this is a person, and a very small part a person is looking at here. This person is here. It is very difficult. Road sign, very small part of the image. And if you want to try to understand what this sign indicate, that's very, very difficult, right? Yes or no? So this person is facing toward this side, this person is facing toward this side. So you can try to understand how different kind of problem is it and how it is difficult for a computer to understand what does it contains. Yes, are these problems are complex or not?
Yes, sir.
Hmm. So that's why we need larger networks, lot many features, millions of parameters, so that we can learn these non-linear problems and complex problems. And CNN will help us to learn these features automatically. It is very difficult to do it using handcraft engineering approaches. Earlier, in the earlier era before 2012, peoples were to solve a specific problem, they were designing specific set of features, right? But with the evolution of the CNN, there is no need to now design handcrafted features. Okay, these filter will automatically learn a kind of set of features for a particular problem that we want to solve. So in real world, you will see this kind of data. Hmm? Viewpoint variation. The image might be captured from a different view. Scale variation. That is the biggest challenge that these networks could see. You're going to if you pass these kind of images to the network to understand, and sometime you'll say this is again a person, but you can see there is a lot of scale variation, and here it need different kind of learning, different kind of parameters. Illumination, another challenge in the environment. Background, right? Deformation, occlusion, okay. Intra-class variation. So lot of challenges in the real world. If you want to solve any real world problem, there would be lot of challenges like this. So that's why it is very, very difficult to make up one perfect model that can solve any problem. That's why we need different type of models to solve different kind of problems. Okay, so ImageNet challenge. You have heard about this ImageNet challenge.
Yes, sir.
Okay, so there is a large ImageNet data set actually, and every year they used to perform a challenge, but I don't know nowadays it is happening or not. So in 2010, 2011, 12, 13, 14, and 15, so on. So you can see this is the error rate actually. So this is how it was coming. It has actually 1000 different classes. Okay. And it is very difficult to classify particular image into particular class. And there are some images that with our naked eye, even we are not able to understand whether to which class this belongs to, this particular image. Okay. So so in 2012, the AlexNet came to the picture that become the beginning of our deep learning era, and first time it has reduces this error from 25 to 16.4, and then further lot of developments and happens, and then the VGG, very prominent network, that came into the picture. It is of made up of 19 layers, and it was the runner up I think at that time, and it has reduces the error to 7.3. And at the same time GoogleNet Inception network came, and it has reduces this classification error to 6.7. And then later ResNet, that has reduces all these errors to 3.5. And with human I think there is a more error if a human try to classify the image into its appropriate class. So this is, you could see, but as we try to reduces the error, you could see number of layers in the network got increases. It increases computation powers, and it require a lot of trainings, lot of data. So all these things are also there. Okay. So Linet was the first model that was developed by Ian Lucen. You should know the name of this person. Uh, he has developed this first neural or convolution neural network kind of approach in 1998. And whatever he established, we are going to use the CNN today because of his contribution. And he just at that time tried to replace these manual feature extraction. As I mentioned, manual feature extraction or handcrafted features are very difficult to learn for different problems. So this was a very simple neural network, convolutional network, sorry. And the name was Linet 5 as it has 5 different con layer actually. So you could see this kind of a structure of this network. So I'm not going to discuss this in much detail. So VGGNet, are you familiar with this or should I explain? Anyone? Hello.
Please give a
So it
glimpse.
is good if you explain it so that we can
Okay.
recall it again.
Okay. So VGG network again came and it was a better improvement of the LXNet actually. I'm not discussing LXNet because very old network. If you are interested, you can go LXNet, type LXNet 2012 and you could understand that paper. So VGG is very popular if you are attending the deep learning course, then VGG is one of the basic network, but you could see it came in 2015 and we are in 2024. The networks we are working on today's, they are very much different from these networks, but it is a very simple network. That was the first thing. And it won a runner-up of this competition, ImageNet, and it is deeper than AlexNet, and it has 140 million parameters, 140 millions. Okay, it's very huge networks compared to AlexNet or other methods. And this is the general structure of this network. And just for information, you try to Google it what VGG architecture is because in the lab session we will be going to use this VGG network for classification of amnesties. Very simple problem, and we try to learn, understand how VGG net help us to solve that problem. Okay, so this is a kind of a structure of the network. So initially two blocks of 3 cross 3 column layer, 64 filters, 64 filters, then pooling layer. Why 1 by 2? Because it reduces the size of the feature map by half. Then 128 filter, 128 filters, and so on. Then finally you could see there are fully connected layers. So fully connected layer, 4096 neurons, 4096 neurons, 1000 neurons, and then finally there is a softmax layer. Why there are 1000 fully connected neurons in this layer? Any answer? I have already answered to this question. I just wanted to see, are you listening to me or not? Why there are 1000 neurons in the fully connected layer of VGGNet? Any answer?
That many feature extractions can be done.
So feature are extracted from these layers, these filters.
Yes.
Why 1000? Why 1000? Very simple question I have asked. Hmm.
So because it has like 144, 140 million parameters, so
No, these parameters are not defined from here. These parameters are the parameters coming from here. I will show you the next slide. Maybe this one, right? So this is how these parameters are coming up. Means if you have an image of 224 cross 224 cross 3, why 3? Why 3 is here?
because it's a 3 by 3
Size
matrix.
of the filters,
But I'm talking about image 224, 224 cross 3.
depth, sir, depth of the image. Like image height, width, and depth, no, sir.
Yes. So the
RGB.
3 is
RGB.
the, yes, 3 is the depth of the image or channels, red, green, and blue. So every RGB image will be having three channels, right? So you could see when this image is passed to the first layer, there we are having 3 cross 3 con filter of size 64. Okay. So it means what will happen? So 64 times this filter will get convolved over this image and their size is 3 cross 3. When you multiply all these terms, it will come up with these numbers. Okay. And then next again, a 64 feature size will get convolved over to this image and there are total these many parameters. 3 cross 3 into 3 times 64. Next time, the output of this would be basically number of how many, what would be the depth after first convolution, it would be 64, right? So first time there are three only, three channels. Once we will convolve this layer over to this image, how many channel would be there? 64. 64 feature maps would be there. Then next time this will 3 cross 3 cross 64 will again multiplied for how many times? 64 times. Okay, you try to understand this math. Very simple. Okay, remember, always remember, pooling layer doesn't have any parameter to learn. Because in pooling layer, what we are doing, we are not learning any parameter. We are just picking up the maximum value out of that particular region. Next layer again, it has 128 filters. So 3 cross 3 cross 64 into 128 and so on. Okay, so likewise this, it will come up with total these number of parameters it required to learn. Okay, now coming back to the question, why we need 1000 neurons in the last fully connected layer of VGG16, or let me to simplify this, can I change these numbers? Can I change these 1000 to 10 or 5?
No, sir.
Okay,
No, sir, because those are standard ones. The image
No, sir,
size
that.
can be changed, but
okay,
the number of neurons cannot be changed, I think.
okay. Any other answer from anyone?
So I cannot change because these are the categories that like the image is classified into.
You're very right. I think you have given the right answer. We can't change it because these are the number of classes you mentioned. Okay. Why 1000? Can you relate this?
So
We
that's
can
what the
easily look up some output, say the last button FC 4096 is there. No? So simply if you multiply 1000, we'll get some. It is easy to calculate. The silly answer, I'm not sure of
Now,
that.
if it is easy to calculate, then we should have taken 4000 here now. These are
Yeah.
calculation not meant for us. These are the calculation those will be performed inside the computer or network. Hmm? Why to make these calculation easy? So that we can learn. If we have to make them easy, we should not have deepen this network. Now we should have taken this part of the network only. So someone has mentioned we can't change these 1000 because the number of classes are 1000, right? Someone has mentioned this.
yes, sir.
Okay, so I have repeated this actually. So this data set, ImageNet data set, it has 1000 classes actually. Have I mentioned this or not?
Yes, sir.
I remember I mentioned this. Okay. So this ImageNet dataset has 1000 classes and that's why the final layer has been set as 1000. If you want to classify dog versus cat, how many neurons you need here?
Two.
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 If you want to recognize digits 0 to 9, how many classes you need?
10.
10.
10. So based on this number will get changed. So If you can't change it, then how you will use this VGNet to solve any other real world classification problem? That's not possible now. It means it has meant to just solve this ImageNet dataset. No. Okay, so we can modify them based on our need. But if you want to use this VGNet network architecture as it is, then by default it will come like this. But you are allowed to change anything, whatever you are going to see over here. Okay, so we'll design our own network and you will see how we can change them and modify them. Okay, good to go. And always remember the last layer in the classification network would be softmax layer. That will give us the probability for that particular class. Okay, any questions here? Good to go. Am I audible?
Yes, sir.
Okay, are you enjoying the session or it's just again another session where you are not learning anything and just kept yourself on the mute and session is
No, sir.
done?
No, sir.
Hmm?
We are learning,
No,
sir.
sir. No, sir. The interactions are quite nice.
Okay. Okay. The same time with when the VGG came, then GoogleNet was also came in 2015. So they won the competition of 2014 and later it got published. You just try to Google it out, these papers. These are very backbone of the deep learning. You might learn fancy words, LLMs, VINet, but if you're not aware about these things, then actually you won't be able to understand what this deep learning is. If you are working in generative AI, let's say, and you don't know the very basic concepts, then it is very difficult to link those because those networks are built up from these networks only. Okay. So these are very, very basic networks. That's why I've kept in these slides. Also, I talked to Abhilasha and she said students might have a session on this earlier and I can keep few slides, but I think most of the time spent over here. Okay, so let's wind up this quickly so that we can have some glimpse of the latest networks as well. Okay, GoogleNet. So you can see the architect. You won't be able to understand from the diagram, but I will show the main building block of this network. And it has an inception module actually. And why they have designed different kind of module, this module I'm talking about. So, and this module get repeated over and over for how many layers? 22 layers. So it doesn't have fully connected layer. That is another interesting thing. Earlier we were talking every convolution neural network is end up with fully connected layer, right? But you will see this doesn't have fully connected layer. It has only 5 million parameters. You could see comparison to VGG. It has only 5 million parameter and also has less computation power due to this. And it has won this challenge. Okay. So this is the main building block of this network. So in VGG, there was a simple con layer 3 cross 3. But here we have a kind of a inception module and we have different kind of filters over here 3 cross 3, 5 cross 3, 5 cross 5, sorry, 1 cross 1. Can somebody tell me quickly why different size or type of filter and how they will help us? Any, it could be a vague answer. I'm not expecting a right answer from you. And by the way, if you are more interested to understand these concepts, these images are taken from Justin Johnson, Fifi Lee. There is a lecture series completely available on the YouTube, and they also have some good material. Okay. You can go there and try to understand in very depth of these concepts. So any answer? Why different size of the filter? 3 cross 3, 1 cross 1, 5 cross 5?
Because it will have different attributes, like the feature maps that are produced will have more attributes in the 5 cross 5 as compared to the 3 cross 3, and then those can be compared.
Okay, let's say you are uh, viewing an object. Okay. And if you are very close to the object is in just in front of your eyes. Okay. You may learn some of the information about the object, right? If that object is a little away from your eyes, you will try to learn different features of that particular object. And if it is little further away from your eyes, then you will see the complete shape of that object and how it is different from the environment and so on. Yes or no?
Yes, sir.
Is this right? Right? So place any
Yes, sir.
object in your eye, in front of your eye, just very close to your eyes, and you will see, you will just might be able to understand what kind of surface it has, what kind of some prominent information the object is. As you move your object away from your eyes, you will see that there are different kind of features inside the object that one has to learn. So the same idea that GoogleNet has predicted, how same way how humans understand different objects in different environments. So these different kind of filters, when they get convolved over the image, they will try to learn multi-scale features. So I mentioned you earlier, in the real world, the there are lot of challenges of this multi-scaling as well, right? An object in one image could be very small, in another image it could be very large. So how a large filter will help us and how a very small filter will help us, this will give us the answer, right? So that's why we have different types of the filters. Those will try to understand, learn different scale of the information inside the image. And they have designed it specifically. And this is not the one design. Later you will see people have, not people, I mean researcher from GoogleNet, Google, and they have designed different type of inception, module inception, ResNet, and there are a lot of variants where they try to include and modify these layers and try to come up with good more solutions to improve those networks. But this is one of the initial building blocks of the network. Okay. So why it has this kind of shape and why this kind of arrangement, why max pooling is not here, why 1 cross 1 is required, why 5 cross 5 is here, why it is not on the outer side. If you want to understand all these things, you need to go to this paper GoogleNet, why they have come up with this kind of design. Okay. Because there are a lot of explanation and I think we don't have that much time. Okay. So another popular paper that you should be knowing, that is ResNet, very popular methods. And you know what will happen if you have seen VGG 16, it has 16 layer, then VGG 19, it has 19 layer. And same way, let's say you have VGG 152. Let's say it's not there actually. Let's say you have VGG 152. It means it has how many layer? 152 layers. So can you tell me what kind of challenge would be there if it is a network of 152 layers?
Parameters will be more, computation time will be increased, and more precise output we're gonna get.
Right. Very right answer. As we increase the size of the network, the number of parameter will go increase and computation power will get increased. And another problem that would come up is of vanishing gradient and exploding gradient. Very important features to understand. So as the networks increases in the bottom layer of the network, what will happen? There will be no prominent features to be learned by the network. So your gradients. So what is a gradient? Basically, when you when the network after the first epoch generates some output, the error will be calculated, that if it is a 3 and it is predicting 1, then that error is computed and those gradients are propagated back to the network so that the filters can change their weights and biases. But if the network is very large, then what happened? There is a problem of vanishing gradient or exploding gradients. Okay. So it means what will happen? The networks will not able to understand or learn anything. So to overcome this problem, the ResNet was came into the picture. That if you want to increase the depth of the network with so many layers, then it will not work like this as earlier, that we can't increase the depth as it is. Hmm? So one example, let's say they have tried a 20 layer network and compared with the 56 layer network. So you could see what has happened. So you understand this graph, number of iterations as we increase the training error, it is going down. But a 20 layer network is having less error than the 56 layer network. But ideally, it should not be. If we have increased the number of layer, it should have more filters, it should have learned more things, but actually it is not happening. Why it is not happening? Because of the vanishing gradient problem. Okay. And also it is not a case of overfitting. You understand underfitting, overfitting, right? So it is a case of vanishing gradient problem. That's why our network 56 layer network is performing poor than 20 layer network. But we will see there are network ResNet with 152 layers and it is performing much better than VGG 16, 19, Google Net and all. As we have seen in the ImageNet challenge, that ResNet is the winner and it has very less error as compared to other. Why? Because it has one specific modules and that module is called residual block. Do you know what is this residual block? Do you know this? Let me come to here. Any answer? Someone was going to say something. Do you know this residual block? So basically in simple convolution neural network, what we see con layer, the X is the input, we'll see con layer, then we apply ReLU, then con layer and so on. This is how we look the network. But in a residual network, what will happen? This X will go through these series of convolution layers and the same identity, whatever the feature is here, is being passed to the final layer and here they get concatenated. Why we are doing this? Because in the deeper layer of the network, as I mentioned, when the network is very large, there is a problem of vanishing gradient. I mean, gradient is 0. Then there is no back propagation is happening. That's why networks is not able to learn anything. That's why these feature maps, if they're very small in nature, they are passed to the next subsequent module as it is, so that they don't get vanish. Do you understand this?
Yes, sir.
Right? So that's why this ResNet module or residual blocks was very useful in case you are going to increase the depth of your network. Okay. So this is finally how the ResNet module would look like, a ResNet architect, and it has again multiple layers. ResNet 152, ResNet the XNet, ResNet this, ResNet that. You will see there are a lot of variants of this, and people have tried to design in a different ways. So you can see these skip connection, right? These are just residual blocks. Hmm? Okay. And again, no phonic detector layer at the end, only we have just one final classification layer of 1000 neurons that you can see over here. Okay, then, okay, so till now we have just discussed about a very basic CNN architect. Now we'll move to little advanced networks and we'll see how much we will be able to understand. You will get just idea, but I won't be able to help you to understand all these things in this one session. So let's just go through them and let's see how much we can. So, so we have seen this Inception network or Google Net, and we have also seen this ResNet. So the idea of the another network is Inception ResNet. So ResNet has its own capability and this Inception has its own capability. So to merge the advantage of both the networks, the another network came, that is Inception ResNet. So it is again lot of variants. Inception ResNet v1, v2, v3, and you will see they have designed different kind of modules like this. Okay. So what it has a residual block like this, as we have seen earlier. So from this layer to this, the identity mapping or what we say, whatever the feature is here, it will pass as it is. And it has inception module as well. 3x3 of different filters, 1x1 of different filter, right? And so it will help us to efficiently extract the features. There are residual connections. We can deepen the networks. It will give us high accuracy and it is very efficient actually. Okay, so this was the idea behind the inception ResNet module. You just go and look the architecture and you will see. But this is the basic building block of inception ResNet V1 architect. And other variants, and this is just complete version of this. And this, sorry, this is one of the module in this. It has module A, B, C, and then there are some reduction modules A and B and so on. Okay. So, just so if you try to look at this diagram, so this what we have discussed. So it has again another kind of module. Here it has different kind of filter. You could see 7 cross 1, 1 cross 7. You might have not seen earlier, right? So they will learn different kind of feature in comparison to 3 cross 3 and 1 cross 1. Okay. And then 3 cross 1 and 1 cross 3 filters. And these modules are embedded over here. Sorry, this one. Inception ResNet A 5 times means 5 times this blocks will get repeated. Then 10 times this module B, then again 5 times this module C. Okay. And then there are some reduction filters. Those will try to reduce the number of parameter using 1 cross 1 con layer and so on. So this is a simple architecture of inception ResNet V1. Similarly, there are V2, V3 and so on. And you will see variety of the families of these networks are there, and they will try to solve these classification problems. Hmm. Okay. So, what is the main problem with these networks? If we go on increasing these networks, they will work very well. But what the challenge is, there are a lot of parameters, lot of computation power is required, and it is very, very difficult to run these networks on a very small devices. Yes or no? Your mobile doesn't support that kind of GPU that GPU your some particular workstation has, right? Because all these networks require GPU for the computation, very high graphical processing units. So how to overcome this? That is a very big challenge, and also to have a good accuracy, again there is a challenge. So it is very difficult to deploy these models on the edge devices, fog devices, right? So the solution to that is we have a very simplified version of these networks, that is mobile net. Okay, the name is mobile net because it is very effective for edge devices or mobile devices. We can deploy this model on the edge devices, but it does not work in the same fashion like VGG ResNet were there. So they come up with a new concept that is called depth-wise separable convolution neural network instead of simple convolution. So just try to see what this depth-wise convolution is. So we have seen convolution. So what happened in convolution? A filter will convolve over the uh, RGB blocks of the feature map. So one is red, one is green, and one is blue. But here, sorry, the in the previous case convolution process, the filter will convolve over the entire RGB pixels. It will take into account one pixel having RGB values like this. Here it will go like depth wise on R color, on G color, and B color. So it will separate out the depths and then convolve the filters out to that, and then finally perform the point-wise convolution to get the feature map. So if we do like this, there is a less computation power required to process actually. So that's why this mobile net came to the picture, and they have modified ReLU to ReLU 6 actually. There is a complete study behind this, that why they have changed ReLU to ReLU 6. So what is 6 here basically? What is the equation of ReLU? It is 0 comma max. So instead of 0, it is 6. I mean, we will not keep the negative value as a 0, we'll keep it as a 6. So that was the meaning actually. Okay, and its width and resolutions are the hyperparameter for this, like how many width we need and all. And it is very effective for edge devices. And again, it has a lot of variants, mobile net V1, V2, V3, and so on. So you could see V2 and V3 might be, I have not added over here. So V2, again, it has a little different architect. it has a linear bottleneck instead of non-linear bottlenecks. So we have earlier discussed that in the bottleneck layer, you mean to say some intermediate layers, basically where the information is get compressed. So we used to have ReLU layer over there all the times, but they have just tried to replace with some linear activation method. Okay, and avoided this non-linear activation function. Then they have inverted residual blocks. Then they have expansion and projection way. So I don't want to go to the detail of this as this moment. So expansion means basically um, expansion by factor 6 means you will try to enlarge this feature map from this to this size. You could see from 24 to 144 it is coming. Okay, because of this factor 6. So this is a kind of expansion layer inside the network as well. Okay, then depth-wise convolution is being performed, then finally projection is performed and it will give the final results to us. So just try to have this. Then finally efficient net. So this could be might be interesting to you. So we have seen so many networks: mobile net, Google net, Inception, VGG, and this VIT is coming, Clip, Blip, and so many you will see later. So what is this efficient? From the name what it comes, that it work on the concept of compound scaling actually. Hmm? So compound scaling means, so can you tell me, if you want to solve a problem of classifying dog versus cat, and if you want to solve a problem where we have 1000 output classes of different animals, then would you try to keep the network size same or not? What could be the answer to this? Do you understand my question? You have one problem where there are two number of classes, and you have another problem where we have 10 number of or 1000 number of classes. Will you try to keep the same depth of the network, same size of the network, same resolution of the network? Will you try to keep same?
No, sir.
Why?
We can, sir, but for two classifications, it takes little time. But 1,000 classification, it takes computation time more. The same network we can, but the output final layer for two classification it's supposed to be two neurons. For 1,000 classification, 1,000 supposed to be. So it is different.
So so basically what the idea is, based on the kind of problem we're going to solve, according to that, we'll try to design the network. How
Yes.
many layer it should have, what could be the width, what could be the resolution of the images, why we are always giving 224, 224 cross 3. We can give 5 cross 512 cross 512. We can give 1024 cross 1024. So it is up to us what kind of image resolution we want to give, what kind of depth we want in our network should have, and what kind of number of channel we maybe we could work on the grayscale images. Why there is a need to give the RGB images depending on the kind of problem. Okay, we could work on monochrome images. We could work on laser data. We could work on some other type of images. Hmm? We could work on heat maps. We could work on any kind of other problems. So that's why the efficient net came to the pictures, because we tried. Now it is very much clear that these size, accuracy, and computation efficiencies are trade-off, right? If we want to increase the accuracy, we're increasing the size, and this will lead to more computational power. Okay, so that's why we need to understand that for a given problem that we want to solve, how we should predict the right kind of width, depth, and resolution of the images. Okay, so for that, basically inside, so basically we designed one base network actually. Let's say we'll keep the depth as 10. It means it will be having 10 layers, then width of the network, then the resolution of the images that we want, and we'll try to understand how does it perform. And we try to learn these alpha, beta, and gamma parameter and phi, and just try to understand how it is working. If it is not giving us the right performance, we'll try to increase them. We'll try to work on different parameters and feed into the network and try to again see how it is working and so on. So it is kind of a trial and error. And then we'll later see that whatever the parameter work best for the problem, it we will choose those particular model for the to solve that particular problem. So if you see this efficient net has 7 different variant B0 to B7. Okay. And in each they have used different combinations of different depth, different image size, different width of the network and so on. And they are also inspired from mobile inverted bottleneck network that we have discussed last in the mobile net, that is a depth-wise separable convolution instead of simple convolution. And they also have this squeeze and excitation block. That is another interesting block to explore that will help us to actually optimize the problem and to focus on the relevant feature and discard the irrelevant feature actually. Okay, squeeze and excitation block. So why I'm discussing all these with you guys actually, whenever you're going to design your own network, you have to think on how you can build up your own network. Okay. So in research, it is not like that you pick up the network and do it and will do. No, it will not work like that. Every problem has a different network, different things to solve. Okay. So you need to come up with the new design. This might work on 10 problems, but it may not work on 5 problems. It may not work on the problem that you want to solve. So you need to come up, you need to understand why your problem is different, why, what kind of data you are working on, what kind of complexity it has. Based on that, you need to come up with the new design of your network. Okay. So this is what it all. And finally, another popular network is VIT. All of you are heard this term, transformer networks. Transformer networks. Have you heard?
Yes, so it's deployed in ChatGPT, I guess.
Yes, very right. So the chat GPT model that you are using every day to make the assignments and to uh, you're making assignment using chat GPT, right? Yes or no?
So it depends.
It depends, right? So there is no problem in using the chat GPT. I'm not saying do not use it. I'm just saying admit it that we are using it. Okay, everyone is using it actually in somehow. But the problem is we should not forget that if let's say I ask the GPT what is VIT, it will give me some answer. Ultimately, I have to go through it, right? So it will just help us to do the searching in a more efficient way, right? The same thing we could find in the Google as well, but we need to go to link by link and we need to check it. But that is an older method, but that was also very useful, right? So just coming back, transformers are the backbone of these chat GPT, Cloud A, and there are a lot of networks in the market. Those are coming up and transformer is the building block of that. So transformer first came into the NLP problem, but later the vision language models have been taken up them. And I will just give you the just hint that this is the kind of a building block of this. This is a transformer encoder taken is as it is. Someone can mute their mic. Okay, so the idea is to divide the whole image into different patches, and these patches are passed to the network, and finally it will learn these encoding over here using this transformer networks, and then finally print the class of the network. So these are the very recent men, but they're also developed in around 2020 or 21, not that much recent. Okay, so can somebody tell me any recent network, any recent methods they have heard about that is coming in 2 days, 2022, 23 or 24? This is very popular network nowadays and it is doing very well actually. But can somebody has heard any other name apart from this transformer? I'm just coming to that in the next slide, but if you have some answer, you can say. Don't Google it and ask ChatGPT in the simultaneously, huh? Just ask your brain. No answer. Okay, so that is zero shot learning actually. So these are the recent methods like clip, blip, Dino V2, fast clips, and so many others. Okay, go to the web page of transformer. So there is a library transformer actually. Just go to that web page and you will see lot of classification, detection, segmentation networks are there. So what is the idea behind these networks? No need of training. Okay. So that's why I was telling you in the beginning, the network VGG that you're sexting is no longer is going to use, but the concepts will remain same. Okay. So what happened with this zero shot image classification? No training is required. They are already trained on millions or trillion of images for many days on very large scale data sets, and you just give the image and give your class that just ask whether this image has cat or dog present or not. It will give you the answer based in the form of probability. So clip, blip, dino, v2, and there are so many others, those are coming up, and we call them as zero shot image classification. Do you find this interesting?
Yes, sir.
Okay. So just look onto this. What are other zero shot image classification models and how do they work? How they do they look like? And just explore this. There are a lot of applications we have already talked about: facial detection recognition, self-driving cars, automatic color characterization, and so on. And then uh, deep learning tools. So you are aware of uh, we are going to use TensorFlows and Keras, right? But there are other deep learning modules as well available, like MXNet, NVIDIA, CNTX Cafe. Okay, so these are some prominent terms related to these tools, and these are some popular courses if someone wants to go in depth. So I would recommend deep learning specialization by Andrew Ng, machine learning course by Andrew Ng. Then this is what I was talking about. If you want to study convolution neural network, just go to Stanford and type this CS231N and you will see a complete material of this. Then there are some other courses as well, those you can go. Thanks for your time. And I think we are over now. If you have some questions, you can ask, we can discuss, and we'll meet in the next session. Anything anyone has?
If you are having any doubt, you can message in the chat box or you can.
Yeah.
Thank you, Dr. Aman, for your conversation. So I think it will be helpful for the members. Thank you, sir.
Thank you. Thank you. Bye bye. See you.
So I request all the participants to kindly mark your attendance on the link and we will resume our session at 3 p.m.
And Abhilasha, all these students are joining remotely. They are not in the campus, right?
Yeah, these students are joining remotely.
Okay. So what I was thinking, how we'll take the lab session. Uh, maybe we'll talk offline. Okay.
Sir, we will talk.
Okay. Okay. Bye. Thank you.